Hello. Today we're going to be going through an overview of modern approaches to prompting large language models so that you can build performant AI features. Let's start with discussing the sections we'll be walking through today. We'll begin by looking at a benchmark on popularity of different prompting techniques before we move on to zero, few shot, and thought generation techniques. In the middle section, we'll discuss ensembling, self-criticism, and decomposition. And finally, we'll finish by looking at alignment, which can help address bias and ambiguity in large language models so that you can have more robust outputs. As a summary of the key takeaways for this presentation, I think it's important to remember that the best prompt is task specific and it will require iteration. So there needs to be this process of trying a prompt, assessing its performance, and iterating based on its weaknesses. And as you'll see, some of the techniques today, especially the more performant ones, they're at the consequence of adding complexity to the prompting strategy. Adding this complexity means also adding increased latency and costs, especially if it's from using multiple large language model calls. So this necessitates an analysis of the trade-offs between performance and cost and latency specifically, and what is the best technique for your feature might actually change depending how you weight those factors. So you might choose to use a less performant technique, but it's going to be a faster and better UX for your users. In general though, as a recommendation, I would say start with the simpler approaches and add complexity as required when you need to have improved performance. I'd also really like to highlight this recent paper, the prompt report. A lot of the strategies that I'll be discussing today have been collated and analyzed in this paper. It's a fantastic paper, and if you enjoy this presentation, I highly recommend giving it a read for more information. So let's start by looking at a benchmark, and this is taken directly from that prompt report paper. And what it provides us is a proxy of popularity by analyzing the citation counts of different prompting techniques. We'll be discussing most of the techniques in this chart here today. And it's worth noting that often, because it is this proxy of popularity, the more popular techniques are often because they have been more performant or have been more reliably used. So it's often a good idea to start with these more popular techniques before you branch off into more unique strategies. Another caveat here as well is you'll see, for example, the most popular here is few shot learning. This is an umbrella term that encompasses a lot of other techniques. So take this chart as with a grain of salt. But after this presentation, it's worth coming back to this and looking at the techniques and where they ranked in this popularity assessment. So let's start with looking at zero and single shot techniques. And the shot here in zero and single shot just refers to the number of examples that you're providing to the large language model in your prompt. So if we're saying it's a zero shot, it means that we're not providing any examples in the prompt. And to clarify as well, we're referring to the prompt as all of the input that we provide to the large language model. So in general, zero-shot strategies are the simplest. It doesn't require you to come up with any examples. It just requires you to come up with effectively a way to stylize and to guide the language model to generate a specific type of output. This also means that it can be used in some of the later techniques as base components within a broader strategy. So we're speaking today about emotion, role, and style prompting, which are some of these base primitives that you can add in a prompt. System to attention, SimToM, rephrase and respond, rereading, and self-ask. Let's start by looking at role, style, and emotion prompting, and let's look at it in reference to a prompt, an example prompt. So you can see here on the left, I have a prompt that's trying to help me generate some copy for a social media marketing post. And in these prompts, especially in the zero-shot setting, we'll often include several modifiers that are aligned to try and improve performance, because we can view the output of a large language model as being conditional on the prompt. So what you provide in the prompt effectively can bias the output towards a desired generation, where desired is what your definition of desired is in this case. So the first highlight in blue here we have is role prompting. And when we're doing role prompting, we're trying to assign a persona effectively for the model to adopt. And we do this because we actually have seen that this has been associated with performance improvements. So in this case, we have an example that they're a top marketing expert, a copywriter at this agency. You could also be a data scientist. there are multiple types of experts that you can effectively appeal to when you're doing your prompting. Style. This is a modifier that we provide in a prompt effectively to align the nature of the output to something that you desire more. So in this case, we're asking for something that's short and concise so we can use it for our social media posts. And emotion prompting. This is an interesting one. There's been research that's actually found that providing like an emotional appeal to a large language model can actually be associated with improved performance. So this is an example of how you can provide an emotional appeal. It's also worth noting as well that this is something that you can use, but it's also often something that, for example, that nefarious actors will try and do to jailbreak your large language model systems. So for example, like the appeals there that my grandma is dying, please do this thing that otherwise you wouldn't be able to do. So it's worth both noting for a technique that you can employ and also when you're testing your systems to see its robustness against these emotional appeals. System 2 attention is our next strategy, and this is leveraging, or it's inspired according to the authors, by Daniel Kahneman's work on the two sort of state theory of attention. And in the second stage, it involves that more planning phase, whereas the first stage is this more direct, immediate answer. So they leverage this two-stage approach inspired by Kahneman here, where they have a prompt A, which is designed to extract the core questions, the core elements of the input from the user. And then we have a prompt B, which is responsible for answering the question. So we've extracted the core question, and now prompt B is trying to answer that question. We pass that result to the large language model, and we get the output, which is then returned to the user. And in terms of performance, the authors note a 20 percentage point increase on trivia Q&A. So this is something that you could, for example, explore if your specific feature is heavily reliant on answering questions. A similar two-stage approach technique, but still zero shot because we're not providing any examples, is SimToM. And this builds on theory of mind, which involves taking perspectives and making decisions, applying reasoning based on the perspectives of different people to determine an outcome or what people see from their point of view. So again, we leverage this prompt A, prompt B format. And so the input here from the user, which is their input, and it gets collated with the prompt that you're providing, goes to the large language model. The large language model is then going to generate the core perspectives. This is because you've prompted with this first prompt, which is asking it to generate these core perspectives. And then finally, you have a secondary prompt, which asks now to answer the original input question provided by the user and take into account the perspective that has been extracted from the first stage. The output of this is then a answer that it takes into account the perspective of the user, which is then returned to the user. And results here as well, they noticed in a false belief benchmark, a 29.5 percentage point improvement in accuracy over equivalent zero-shot techniques. So this is quite a big performance boost, and it's something that worth noting. It's a general sort of concept, and we'll see these later in the decomposition section, where breaking problems down into simpler sub-problems can often result in performance improvements. Rephrase and respond. It's a deceptively simple technique that has disproportionate performance improvements. So in gray here, I have exactly the prompt format that is recommended by the authors. And you'll see we have the input question that comes from the user. And then we append a phrase to it that is literally rephrase and expand the question and respond. So this now comes in the form of the prompt. This gets combined with the user's input. We give this to the large language model and we get the output, which is returned to the user. You can see on the right here, this is from the paper, the performance improvements associated with it. You see in the orange here, the results from using this rephrase and expand the question approach, that on pretty much all of the problem formats that they tested on, they see improvements. So again, a simple approach that can often be associated with quite a large improvement. Rereading 2, this is another one that is also very simple. So we have the input question, which is provided by the user. Then we ask in our prompt to read the question again, And then optionally, we can have a thought eliciting instruction. So this could be, for example, a chain of thought approach. And you will see in subsequent questions some examples of these thought eliciting approaches. The process is the same. We provide this as input to the large language model and we get our output. Performance improvements, more modest, but often actually this level of percentage point improvement can be quite meaningful from a feature perspective and translating into actually users enjoying using your feature. Self-ask, this is another two-stage approach. So let's begin with stage one. In stage one, we take the user's input and we have a prompt that asks it to generate a series of interim questions. We then move on to taking these interim questions and we can either provide them to another large language model call, or for example, you could use an external tool like the web to generate an answer for the interim question. We then can move into stage two after one of the following occurs. So we reach a max questions condition, which effectively could be a hyperparameter that you set. You could say you can maximally ask 5 more questions, or it could be that all of the interim questions have been answered. Either way, when this has occurred, we move into this stage 2 approach. And in the stage 2 approach, what we provide is the original user's input, as well as now the question answer pairs from stage 1. So our prompt now says, based on this input and question answer pairs, actually answer the question. This output then is provided to the user. So that's been a lot of the zero-shot techniques. There's obviously a lot more that you could employ, but there are a few representative examples. If we now move on to few-shot, which effectively is just any prompting example, any prompt that uses 2 or more examples in the prompt, then there are several new techniques that we unlock. And we'll speak today about self-generation, retrieval, vote case selection, prompt mining, example quantity, ordering, label distribution and quality, as well as the example format. So let's start by discussing the examples in few-shot examples and some of the common considerations for them. Firstly, how many examples should you provide? Research has indicated that in general, there is a positive correlation between the quantity of examples that you provide and performance, although there are diminishing returns to this. And one of the major papers that looked into this found that, for example, after 20 examples, there's typically near zero further improvement. It's worth also considering from a business perspective, the more examples you provide means the more input tokens, which also means additional cost. So you should look to find a number of examples that gives you the performance that you want and then not necessarily extend beyond that. Now, the ordering. So unfortunately, large language models can still be quite brittle, especially for some of the older models, which are typically smaller in size. The order that you provide your examples in have been seen to, in literature, actually impact the performance of the system. So it's important to firstly try out different orderings of your examples. And then if you are using a specific order sequence in your testing phase and then you move to production, make sure that you use the same ordering sequence in production. Otherwise, the performance may be disparate between testing and production. Label distribution. This is a classic problem from machine learning, and it's the same here for prompting large language models. If you have a bias towards one certain class, so let's say, for example, we're trying to do a prompt for fraud detection, and we have 19 examples that are fraud and only 1 that is not fraud, your generations will be biased towards predicting fraud. So as possible, try to do equal label distributions or label distributions that are representative of the actual task. The quality, this is also, I think, quite expected. But if you are providing examples and they're labeled examples, so for example, again with the fraud case, you give an example and you're saying it's fraud, but it's not actually fraud, then that is going to negatively impact your performance. So it's important that these examples are labeled correctly. Format and prompt mining. So research has found that how you format your prompt grammatically, structurally, can actually influence performance. So then the question arises, how can you determine what format that you should use? And there's a technique called prompt mining to do that. And in this prompt mining approach, effectively what they've done is they've tried to identify common structures that have appeared in the training data set, and then using these common structures in the examples. This has been associated with improved performance. So in general, You should try and know what data your large language model has been trained on. For a lot of commercial ones that you don't know, as a proxy, you can look to see how other people are prompting these. And in general, if there's a consensus towards a specific structure, so for example, a question answer structure could be Q colon the question, A colon the answer, then you should look to adopt those common strategies as opposed to coming up with your own unique interpretation. That's obviously not always going to be the case, but as a general rule of thumb, adopt more common structures. And similarity. This is again a classic one from just general machine learning as well. The examples that you provide in your prompt should be reflective of the type of examples that you are requiring this AI system to solve in production. If there is a disconnect between those two, then the testing, the evaluation that you have done in the prompt evaluation phase will not fairly extrapolate to what you're seeing in production. So you want to make sure that it's a representative example that you're providing. Okay, let's now talk about self-generated in-context learning. And effectively, this is a way of generating synthetic examples. So coming up with the examples, we've just spoken about how it's important to have them and it can improve performance, but coming up with them by hand can be quite labor intensive. So thankfully, research has indicated that actually using a large language model itself to come up with examples that you then use still is quite performant. So the benefit of this is it's really easy to do. You just make a prompt and ask it to generate an example. The disadvantage, though, is there is, or at least from this research, has been a performance degradation identified. So from their research, they identified that a synthetic example is worth about 0.6 real human-generated examples. A caveat that I'd like to note for this, though, as well, is that for larger, more recent models, this performance gap may shrink. So it's worth still checking this approach on some of the more recent models. As a note on, terminology here as well, you'll often see few-shot learning also referred to as in-context learning. It's effectively the same thing here. Okay, so now we need to think about how do we select examples. And this, this is a general sort of framework, a general question that you need to answer to support a lot of different techniques. And how you do this selection process actually demarcates, it identifies a lot of the techniques that we'll talk about later. So in this section, I'm going to be speaking, more generally about a framework that you could use for selection and then eventually retrieval. But just note, as we go to the other techniques, they'll supply their own algorithms to do this selection. So let's say for this example that we start with a data set of unlabeled examples. So these are just say again for the fraud case, a bunch of examples, but we don't say whether they're fraud or not, etc. You can think of any sort of, example that you would provide for your specific feature, but somebody hasn't gone through the process of actually reviewing these examples and saying this is associated with outcome X, class X. So we have this, and now we need to create a selection algorithm to effectively choose examples from this unlabeled data set that we then annotate. And there are multiple approaches to do this. The paper that I have at the bottom of this slide proposes a method called vote-k. And other papers will provide different methods. At a high level, what this vote-k algorithm is doing is it's taking all of these unlabeled examples, it's generating an embedding for them. You can think of an embedding as a semantic representation of the meaning of that example, and then it's creating a graph. So each of these examples become effective, or their embeddings become a node or a vertice, and then we connect it to its k closest based on a distance metric. So the paper, they use cosine similarity, and then we connect that graph that way. So we create our graph, and then for each of the nodes here, we evaluate a score for these examples, and we choose the ones that have the best score, where that scoring mechanism again is something that different papers will provide a different mechanism for. Once we have that scoring mechanism, we'll effectively use this to generate a pool of candidates to then annotate. There are a few more steps here in the vote-k algorithm, but that's the sort of the core component to understand. You have to come up with some way to effectively choose a set of candidates from your unlabeled data set that you should then label. So let's say we've done that, and we've now got a smaller data set of unlabeled examples still. We then choose these for a human to annotate them to get examples. This might not always be the case, but if you are going to use humans, this is a more efficient way of doing it. Another case could be, for example, you just still don't worry about labeling them. So now we have our labeled data set, and we need to associate this with a retrieval algorithm. We need to associate this with a retrieval algorithm because we want to pull in examples to then use for our few-shot prompts. So there are multiple ways that you could do this. For example, you could use a k-means approach. You could use, again, similarity metrics like cosine similarity, Euclidean distance, or distance metrics. But the idea is the same. You're trying to retrieve examples that are relevant to your specific problem at hand. So for example, the k-means approach, you would have clusters of these data sets based on their semantic meaning. And then you could choose what cluster that your input example is, your input from the user is most similar to, and take those examples. Let's make that a bit more concrete. So all this approach that I've shown here, all this part of the framework can be done offline. It can be done beforehand, and you can store it as basically static values. Then when you're using this, system in production, a user comes along, you have your prompt for it, which is effectively a prompt template that you want to add examples to, and the user has their input. We take the user's input, we provide this to the retrieval algorithm, we run our retrieval algorithm, and we get back the examples that we want to use. So now our input to the LLM is going to be this prompt with the provided examples now that we've retrieved and the user input. It goes to the large language model and we get our output. So effectively, what's on the right-hand side of the screen is what is done at runtime. And that's actually a very sort of simple approach that supports this few-shot prompting. And then on the left is everything that we do beforehand. Combining this means it's a way to effectively and efficiently find the best examples from what could be a large data set of potential examples or raw data that you have to support a few-shot system. Okay, now let's speak about the topic of thought generation. And this has actually gained a lot of popularity, a lot of the techniques here. The whole idea around thought generation is basically coming up with techniques that, induce the large language model to specify its reasoning. And the idea that specifying its reasoning is associated with better performance as opposed to just directly outputting an answer. So one of the most popular techniques, and that a lot of later techniques build on, is chain of thought. We'll speak about that. We'll speak about analogical prompting, automatic chain of thought, thread of thought, step back, active prompting, complexity-based, contrastive chain of thought, uncertainty routed chain of thought, and memory of thought. Let's first start with chain of thought. Zero-shot approach. So this can be applied in a zero-shot or a few-shot setting. In the zero-shot approach, there are multiple ways that you can do this. The most basic is just using a thought inducer. So from the original paper here, the thought inducer that they use is let's think step by step. So it's as simple as adding this to the end of your prompt, and this will induce this chain of thought prompting. Secondary approach is step back, and in this we first ask the large language model to answer a related high-level question before moving into the reasoning phase, and this has had performance improvements empirically. Analogical, we won't speak about this in too much detail. In general, this is another approach for, synthetic data creation, and it's a way of automatically generating these chain of thoughts, which could then be used in a few-shot prompt where you provide multiple chains of thoughts. Where again, a chain of thought approach here, in its more complete form, would be a input question, a rationale for answering it, and the ultimate answer. Thread of thought. This is another one where it's as simple as appending a set of text to the end of your prompt. So what the authors propose in that paper is walk me through this context in manageable parts, step by step, summarizing and analyzing as we go. And I think this is a good moment again to highlight that we can view the output, the generation of the large language model, as being conditionally generated based on the prompt. And we're trying to predict effectively the most likely sequence based on this prompt. So this is why providing this type of text in different prompts can actually still improve performance, because you are conditioning your generation on what you're providing in your prompt. Tabular chain of thought. This just uses a thought inducer, a general chain of thought approach, but what it has is also an output instruction that asks it to do its reasoning in the form of a markdown table. And the authors in this paper hypothesize that by imposing this structure on the output generation, it is also going to be associated with improved reasoning structure and logic, and ultimately performance. Let's now speak about active prompting. And the thing that I want to highlight the most here is its introduction of this disagreement metric, because this disagreement metric is something that you can use in the process of selecting examples from that framework we discussed earlier, as well as being a general metric that you can use in, for example, an ensembling mechanism where you're trying to choose the best of multiple outputs. Okay, so how this works effectively is we introduce this uncertainty estimation to select the example questions. So if we look at the diagram on the right, how we could get this disagreement, this uncertainty mechanism, is we can have a prompt, and then we pass that to the large language model, and then we get an answer from that. We can repeat this multiple times, in this sense k times, to get k different answers. We then calculate the disagreement score between these different answers by using the below metric. So if we convert the answers that we've gotten to a set, so that means every answer in there is unique, and then we take the cardinality of that set, which is the number effectively of unique answers, and we divide that by k, which is the number of iterations that we did, then we have a formula for what we call the disagreement score here. And so I guess if every single answer was unique, then the cardinality of the answer set would be same as the number of iteration, and your disagreement score would be 1. So in the sense that this is 1, it indicates higher disagreement. The assumption as well that they use for motivating this is that if there is a higher disagreement, then we're expecting that the example itself is more challenging. So in the selection case, this could mean that these are good candidates for selecting and human annotating, because the large language model is currently struggling with it. In general, this idea of trying to find examples that are challenging based on the disagreement or how many of them come up as the same answer is a technique that actually gets used a lot, especially in the later ensembling methods. And we'll discuss, I guess, the core motivation for using that approach when we get to that section. Okay, now we're going to talk about automatic chain of thought. Specifically, we'll speak about the streaming approach that they suggest in the paper, because I think it's probably the more interesting for a production-based setting, and also provides a complete example of the basic chain of thought approach. This technique is designed to generate chain of thoughts that you could then use for a few-shot prompt, basically in an iterative manner. So we start in initialization phase, and from this we have our set of questions. So these are example questions. You could have them as your part of your unlabeled data set. Then we perform a zero-shot chain of thought on them. So for example, let's think by step using a thought inducer. We then, as output, get our chain of thoughts here. So we have the question, the rationale, and the answer. We store each of these in a demonstration set. Then, once this initialization phase is done, we can actually perform few-shot chain of thought. We take the questions again, and we take the demonstrations from before, and we inject these to now support few-shot examples for our chain of thought. We get now from this process a question, a rationale, and an answer again. And in the streaming sense, we can update our demonstration set to now include these values that we have just created. Or in the sense that we are providing this to a user, we take the answer from that chain of thought and we provide it to the user. So again, why do we want to do this? It's because we have found performance improvements from providing examples and from the few-shot approach as opposed to zero-shot. This is a way to do that in a more easy and flexible manner. Okay, complexity-based next. This is another one where I think the core thing to understand here, and for your, I guess, extra prompting techniques it's worthwhile having some knowledge of, is that they introduce this complexity heuristic and do this majority vote based off it. So just like how we had disagreement score before, we now have a complexity metric. They provide a few examples of heuristics that you could use for this. So in the paper, they use their heuristic as the number of reasoning steps in the chain. But you could also do, for example, question length or response length as a measure of your complexity. We can then do this to support a majority vote approach. So a majority vote where we're trying to get a consensus between them. We can do this here. So say, for example, we have our input and our prompt. We provide this to n distinct large language models. They can be different models, or it can be the same model, but just different calls. We get n generations from this approach. And then we filter these n generations based on a complexity heuristic. So for example, again, we're saying, let's say k is 4 here, or k is 3, better for this example. We choose the k examples from there that had the maximum score on the complexity metric here. And this is the assumption that higher complexity is going to be more relevant to condition upon for your few shot prompt. So you take your candidates now, and then we perform a majority vote based on them. So when majority vote is saying, looking at these answers that we've had, what is effectively the most common answer. So to iterate again, we've got n generations. In our prompt, we are providing this to a complexity heuristic, and we're going through the logic that the more complex chain of thought is going to be more performant, and we then do the majority vote based on it. Contrastive chain of thought. This is an interesting one, but I think also quite intuitive as well. So in the chain of thought approaches that we've spoken about before in the few shot settings, we've, I guess, implicitly assumed that the chains of thoughts that we provide as examples are valid chain of thoughts. So that means they come up with the correct answer. But what this paper suggests is that you should also provide examples of incorrect chain of thoughts. Importantly, that they are labeled though. So we say this was incorrect logic, this is why, so it's not a valid output. And what they find actually is improvements in reasoning across a lot of major categories. We'll discuss these major categories and how it improved, but before we do that, we need to, I guess, briefly explain what are objects and language in the context here. So we can think of our objects as our symbolic items. So these could be the numbers or a person's name, and we're referring to language as the surrounding text that outlines the reasoning and the interaction with the objects. So now we can talk about what are actually some types of invalid chains of thoughts that you might want to provide as examples. Firstly, we have the reasoning case. This is the most obvious and basic. This is where the conclusion that has been drawn, the answer doesn't actually follow based on the rationale that is outlined in the chain. We then have the idea of incoherence, and this is the case when either the objects or the language has not been ordered correctly in the steps of rationale. So this could be, for example, inferring A has happened, but for A to have happened, we need to have had B already happening. So the ordering of A and B there are incorrect. Irrelevant objects is quite intuitive. So for example, if we're trying to perform a chain of thought that's answering a question related to a product that your company offers, but then in this chain of thought, the model starts speaking about another product that you offer that is unrelated, that would be considered irrelevant. So for few shot prompting, to summarize what this paper suggests, is you can provide both correct examples of chain of thought as well as incorrect or invalid chain of thoughts that are labeled such. Memory of thought. This is an interesting technique, and I think, again, the most important thing to consider here is how they're establishing this memory bank effectively. So let's step through it. So firstly, again, we take this unlabeled data set. So this can be a form of selection and retrieval. We generate chains of thoughts for each of these unlabeled data sets. And then we pass them through a confidence mechanism where we filter out those that have a uncertainty that is above some predefined threshold that we want. And then we store these effectively as a bank of memories. So that's the memory of thought part. And then at runtime, we can retrieve these memories and use them as few shot prompts examples. So let's see here how they're proposing to do this, like, I guess, confidence or uncertainty-based thought filtering. Again, we have our data set, we generate chain of thoughts for each of them. We now have to do this confidence estimation phase, and they propose doing so via answer entropy. And so in here, if we talk through the formula, they're having U representing the entropy here, and a higher score for this answer entropy means greater uncertainty. So we would filter out those with a higher score above a threshold that we define. So if we define A star as a set of all of our possible answers, so now this includes our unique answers, and if we have the lowercase a as being a specific answer in that case, We can calculate the probability for it by doing a sum of effectively the number of cases where this answer, this lowercase answer, is generated in this set, or from the set of all answers. And then finally, we calculate the entropy using the standard formula for entropy, which is a measure of uncertainty inherent in the generations. We then now have this mechanism, this score, and you can see here how this gets filtered to then create your bank here of memories of thought, which at runtime you retrieve to ingest as your few shot examples to your prompt. Okay, uncertainty routed chain of thought. This was introduced by Google in the Gemini papers. It's actually quite a straightforward approach. So what they do is they conduct standard chain of thought prompting. They do this k times, and they define a threshold on confidence, which is a metric that they use. They then perform a majority vote, and if the confidence threshold is met, then we return that majority vote. Otherwise, we fall back to just doing a greedy approach, which is where we choose the most probable of the generations. And remember, when we're doing these generations, we can get probabilities from them. This is from their paper directly, the performance improvements. Again, more modest improvements, but this type of, I guess, small percentage points in a large scale feature can mean a difference between a user getting the correct answer or not the correct answer. So it's worthwhile still exploring things like this as a general idea. Okay, the next category that we'll be speaking today about is ensembling. This is a family of techniques where the goal is to use multiple prompts, get multiple generations, and then via some mechanism, aggregate these generations to get a final answer. Ensembling actually is a technique that's very popular in more traditional machine learning, especially in competitive machine learning. It's often associated with getting the best possible performance out of a series of techniques. But there is a trade-off here in that because we are now for every prompt, let's say, for example, if we're ensembling k different approaches, we are then also having to do k different generations. You can parallelize this, but you're still going to incur the k costs for it. So often it can be that ensembling can be hard to implement in a way that is cost and latency effective. That being said, if you're really looking for performance, you should still consider this. And as language models become cheaper and faster, this becomes a more relevant strategy. So we'll talk today about consistency, consistency-based self-adaptive, universal self-adaptive, diverse, max mutual information, meta-reasoning, mixture of reasoning experts, and demonstration ensembling. Let's start with consistency. And this builds on, I think, what is quite intuitive logic. And that says that if we're having these multiple large language models, or just in general, if we have multiple people answering the same question, if the answer is truly correct, we should expect that multiple generations or multiple people coming up with the answer come up with the same answer because it is the correct answer. And that means that if we're getting a lot of disparate answers or something that only comes up every now and then, it's more likely that that's not going to be the correct answer. So consistency basically leverages that idea and applies it to large language models by often doing things like, for example, using a majority vote. And so majority vote can be viewed as a way of implementing consistency because it's looking for the most consistent answer out of the series of answers that have been generated. Prompt paraphrasing is a technique associated here with self-consistency as a way for generating these different prompts so that you can generate the multiple different, chains and eventually answers. Simple approach, data augmentation, prompt the language model to alter or paraphrase parts of the original prompt. Now, universal self-consistency is just a generalization of self-consistency. So you can imagine the majority vote mechanism is quite attractive. But it can be challenging because you have to determine how do we tell whether two answers are the same. And especially if we're doing like free-form text generation, this becomes quite difficult. So with universal self-consistency, what we do instead is we create a prompt template that takes in these answers from the different generations, and then it leverages a large language model to ask it what is the consensus here, what is the majority vote. So it's a more flexible approach that can still be quite performant and help alleviate the case where you can't clearly programmatically say these two answers are the same. Meta reasoning over multiple chain of thoughts, it's very similar to universal self-consistency, but instead of in the prompt template just having it work based on the answer from all the individual levels, it doesn't assume that there is necessarily an answer that is existent, and it will take the whole chain of thought from the examples into the prompt template and then ask the LLM based on these chain of thoughts, what is the most common answer. Okay, consistency-based self-adaptive. This is another technique that we can use for selecting examples from a candidate pool to then use for few-shot prompting. The most, I think, interesting part here is to think about how they're doing this factoring in of consistency, entropy, and similarity to choose these relevant examples. So let's step through how it goes. Effectively, we take a series of questions. We again generate the zero-shot chain of thoughts for them. And then for each question, we calculate the majority vote. So if we step through this out here, you can see here each question we've generated multiple chain of thoughts for each question. We're then seeing if they're correct. And again, correct here is being what is the majority vote. We filter these down to only the chain of thoughts that had the resulted in the answer that was the majority of vote. And we store these in our global candidate pool. We then need to turn these global candidates into a smaller set of samples to use for our few-shot prompting. And the paper proposes the following approach. So we first calculate a question score for each candidate. So this is based on the question only and the associated chain of thoughts with that question. And we calculate its score for the candidate as being the normalized entropy of the question itself, plus a penalty associated for repetition of the reasoning path. So of the chain of thoughts for that question, we penalize chain of thoughts that are very similar to others. So we have this at the question level. We then are now trying to generate our sample level ones. So how we do this is we first have to start with an empty set, which is our samples, our empty set there. And we initialize it by taking the candidate that minimizes the sum of the individual question scores plus a new repetition score penalty that compares the candidates to the sample values we already have. So in the case when we're initializing, because there are no sample values already, we're just going to be taking the minimizer of the question score. But then going forward, as we build out these series of samples, we're now going to be assessing every candidate based on how similar it is over to the other candidates that you've already set in your final sample set. So what this does is it means that we factor in consistency and similarity. So we're looking for examples that are more diverse in their reasoning. And we also take in the entropy associated with the questions as well. So we do this process, and you can see here how the question score comes through in both to get our samples. These samples can then be used for supporting few-shot prompting. Okay, next we have universal self-adaptive. This is an extension of the prior technique, which is also referred as COSP or COSP. And what we do in this process is we again generate these stage 1 outputs, which are the zero-shot chain of thoughts. But now we introduce a task-specific selector. So what they do here is, for example, whether you're doing a classification or freeform generation, they have a task-specific selection algorithm here, and this is what is applied. So that differs from the prior, where we always use that same approach of using the question score and the repetition penalty. Now we have different techniques based on the use case, and you can look at the paper for the different ones that they propose. So now at inference time, when we're actually running this, we have our prompt, which we provide, as well as the user's input. We then get our relevant examples from the output of our sample set, which was given by the task-specific selector. We provide this whole block of information to the large language model, and we get our output from that, which is returned to the user. Okay, next we'll be speaking about demonstration and diverse. And what we find here is that generating multiple responses based on different prompts and then aggregating can improve performance. So this is just the core idea of ensembling here. So in demonstration ensembling, what we do is we take a series of examples. These are called demos here. So I have demo 1 to demo 6. And we choose a subset of those examples to do a few-shot prompt with the same user question. So here I've done this 3 times. The question is the same each time, but they have different examples. We pass these to a large language model, and because I had the three inputs here, I get 3 answers, and then I need to ensemble them. So what they provide in the demonstration paper is multiple techniques to do them. Some of the ones that they highlight is, for example, doing a product of experts, a mixture of experts, and just taking the max most probable. So you can think for a product of experts, it takes the probability associated with all of the answers. The mixture of experts, it requires us providing a weight for each answer, and the max is, again, like I said, just choosing the most probable of the answers. The verifier on reasoning step is at the start relatively similar to approaches we've seen before. We have 3 prompts, we take it to a large language model, we generate 3 candidate chain of thoughts. What they then introduce is this idea of a step-aware voting verifier and the majority vote. Because the step-aware voting verifier is more unique to this paper, I'll discuss it more here. Effectively, the logic that they build upon is, whilst a chain of thought might produce an incorrect answer, there can be differing degrees of how incorrect it is. So for example, a chain of thought might get the ultimate answer wrong, but one of its initial steps of reasoning in its rationale was actually correct. And we might want to leverage these correct reasoning steps in the ultimate answering of this question. So the step-aware voting verifier is aware of these different rationale steps and can take the ones that are still correct. The majority vote here and the step-aware voting verifier gets combined into a classifier that they train for determining the best possible answers. We then return the answer based on this. Max mutual information and more. So max mutual information is a technique for getting the best prompt template to use. This is something we discussed earlier, how providing different formats for your prompt, or templates in this case, can have differing impacts on performance. Max mutual information provides a technique for determining what is the best template to use. And what they do for this is they build upon the idea of mutual information, which tells us the reduction in entropy. So you can think of this uncertainty related to it, observed in one random variable when the other random variable is known. So in this case, it's when the prompt is known, what is the impact to the entropy of the overall system. And we should assume that a prompt that results in a higher max mutual information is going to better align the large language model to the task. They prove empirically that this is the case. Next, let's speak of mixture of reasoning experts. This is quite a flexible approach. So here I have D experts. These experts could be, for example, a different prompt, or one could be doing a RAG, a retrieval augmented generation pipeline. Another could have web search, etc. They have these D experts in this case. You get answers for all of them, and you select which is the best answer out of it. So in this paper, what they train is a classifier for determining the best answer from there. But you can think of this as an area where you can experiment with different classifiers. So you might categorize the input question as being more related to expert B, and therefore you want to weight expert B's answer higher than the others. In general, what this answer selector refers to is a way of determining out of these D expert answers, which answer should I take. Because this classifier gives us a prediction. In this paper, what they do is effectively say if there is enough confidence in the prediction, they return the answer. Otherwise, they can choose to abstain from providing an answer. In general, this idea of abstaining or falling back to a generic answer when a language model doesn't know, or when your AI feature doesn't know, is something that can be quite useful. Often the downside of not providing an answer versus providing an incorrect answer is such that not providing an answer is a better way forward. Okay, next we'll be speaking about self-criticism, and this is quite a flexible technique which can be leveraged alongside the other techniques that we've spoken about before. Effectively, what it involves, and this is the self part of the self-criticism, is getting a large language model to assess its own outputs and performing actions based on that, where the actions that are performed are done programmatically. So we have chain of verification, self-calibration, self-refine, reversing chain of thought, cumulative reasoning, and self-verification. So 6 topics that we're going to be discussing today, or 6 techniques. This paper, or these papers, build on the identification that large language models are actually quite performant at identifying errors and when something has gone wrong. And so we can leverage this and we can create more robust systems that improve outcomes. So a few of them that we'll speak about first in this section. Firstly is self-calibration. And this is the most basic, effectively, of the self-calibration approaches. All we do is we generate an answer or generate a series of text, and then we do a subsequent call where we ask the LLM, is the prior response correct, or is it aligned with our initial instructions? Self-refine extends this further to get the secondary LLM to also provide feedback on the initial answer. And then we can prompt another LLM to improve the original answer based on the feedback. This can be done in a loop, or it can be done in a single example, and you can define your own stopping criteria for when we've done this refinement process enough. So for example, you could have a maximum number of refinements, or you could have some other metric. Self-verification. This is an interesting approach. So first we generate multiple chain of thoughts. And then what we do is for each of these chain of thoughts, we effectively hide or we mask one of the rationale steps, for example, and we ask a large language model to, I guess, fill in what was masked, and we use this as a score. So based on this ability to reconstruct, we score the different chain of thoughts, and then we take the chain of thoughts with the highest score. The intuition here is so assuming that the chain of thought flows properly, flows logically, and is correct. In this self-criticism step, we should be able to infer the step that would have been required to get to that next part of the rationale. Reversing chain of thought is similar to self-verification in that it leverages chain of thoughts, but it's a bit more, I guess, comprehensive. In that what we do is based on a candidate chain of thought. So in this case, where we only have the rationale steps and the answer, we ask a large language model to generate the initial question. And again, this builds on the intuition that if the chains of rationale are logical and the answer is sound, then we should be able to infer what the original question was by going backwards, traversing backwards through those reasoning steps. What they do as well is they provide an additional step on the end, which is if there are inconsistencies, they get a large language model to improve upon it. Cumulative reasoning. This is an approach we've basically spoken about before, but why it's handy to discuss here is that they name a few of the terms, which can make it easier to discuss these systems in general. So they have the first step, which is generating the steps to answer the input question. We refer to this, or they refer to this in the paper as a proposer. They then have a verifier, which is the job to evaluate whether previous steps are valid. So that is the self-criticism part. And finally, we have a reporter, which effectively is responsible for terminating. So when do we have enough reasoning that we're happy with that we can stop now? So effectively, to summarize, proposer generates the steps, verifier evaluates the steps are correct. We then do those steps, and our reporter says when to stop. Next, we'll be discussing chain of verification. This is, I think, a relatively actually simple example, but it's a good illustrative example of how some of these self-criticism techniques can work. So we can see here the first stage is generating a baseline response. We then provide this baseline response to a large language model to get a verification plan. So this is what do we need to verify. We then execute that verification plan. So can be using a large language model or could be using some programmatic implementation. And finally, we take the output of performing that verification plan to a large language model to get the final output, which is conditional on the previous verifications to the user. Decomposition is the next topic that we'll be speaking about, and this is something that we've already alluded to before, and it builds on the general logic that a complex problem for large language models can be challenging to solve. If we decompose or if we break it down into smaller problems, they can be more manageable. And then by aggregating these smaller problems, we can have a better ultimate outcome. The techniques that we'll be speaking about are, in general, decomposed prompting. This is a technique for decomposition, not just decomposition in general. Faithful chain of thought, least to most, plan and solve, program of thoughts, recursion of thought, skeleton of thought, and tree of thought. First, let's talk about plan, solve, and program of thoughts. Firstly, with the plan and solve, this is an example of a zero-shot way to do this decomposition process. In the example section here, I have exactly the text that is recommended from the paper, and that's let's first understand the problem and design a plan to solve it. Then let's carry out the plan and solve the problem step by step. So this is another example of how you can want to use a technique. So for example, you want to use decomposition, but you can start off at a simpler approach, which is the zero-shot version here, which requires just a small modification of your prompt before you necessarily have to do all of the system design work to actually divide your problem into multiple and solve independently. Program of thoughts. This is another example which is quite straightforward in that we have our initial prompt and the user inputs. In our prompt here though, what we're asking is for the language model to generate a series of code instructions that we can then run to effectively evaluate this. And the idea being that if we can programmatically evaluate it, this should be more robust. So once we get this program out of it, we can either directly run that program and get our answer and return it to the user, or the output from the program can be provided to another large language model to get a better text wrapped answer to send to the user. And again, the idea here is decompose. What are the weaknesses of the large language models, identify, put them into a system that can better handle that, then aggregate back together. Okay, so these next two go through that process of, again, break it down into sub-problems and then aggregate. It's more tractable in that sense. So for the least to most approach, what they do is they first define multiple sub-problems using an LLM to get this and a prompt. And then for each sub-problem, we sequentially try to solve them, again using prompting. And the sequential part falls in that in each time we are prompting the large language model, we take the input and the results of the previously solved questions. And then this final answer is a result of the solving the last problem in this cumulative approach. So we'll also speak about recursion of thought, which is similar to least to most, but it leverages the idea of recursion. And that is what we do is we try and identify what is the challenging problems using a prompt and in the chain of thought. And then for each of these challenging problems, we trigger another process which performs the recursion again to generate chain of thoughts, identify the challenging problems in it, and ultimately come up with an answer. We then bubble this answer back up and feed this into the original prompt template as now just the answer. Our final output is conditioned on this filled in prompt now with the answers. So the idea is instead of trying to get it all done in a single call, we have this recursive process where it breaks it down into these simpler, manageable, tractable sub-problems that it can solve and bubble back up. Okay, next we'll speak about how we can use some traditional programming to increase robustness of these. And specifically what I want to talk about here is now using tools. So in this paper where they proposed decomposed prompting, what they suggested is identifying different tools that you want to help with the feature or performance of that feature, and then prompting your large language model to use those tools when necessary. In general, this technique has become a lot more viable, and it's actually a very popular technique. A lot of, for example, it's got a lot of use in agentic type work because now we're seeing more commercially available models, fine-tuned models for using tools, which means they've gotten better at identifying when they need to use a tool for a certain problem. So this technique has become even more viable, and I would definitely recommend looking into it. Faithful chain of thought starts off the same as other chain of thoughts examples. So we have our prompt, our input, we go to the large language model, and we generate, though, a chain of thought. But now we generate what we call a reasoning chain. And we call it a reasoning chain. It's a combination of natural language and symbolic language, and is defined in a way so that it can be provided to a deterministic solver to evaluate this reasoning chain. The idea being that if we are using a deterministic solver, it must be the case that the reasoning chain is valid for the output to come out. Whereas if we don't have something like this that is done programmatically, that is done to make it faithful, then a large language model can generate a chain of thought that is not necessarily valid. The steps don't flow, but it gets the correct answer. So by doing this process, we can improve robustness of the system. So as you see here, the reasoning chain gets past the deterministic solver, which then generates the answer and return that to the user. Tree and skeleton of thought. Tree of thought particularly has gotten quite a bit of interest and focus, and they're interesting techniques because they show us how we can leverage traditional data structures within the prompting framework as a technique for you to deploy, as well as a way to parallelize these approaches. Start with tree of thought. From the paper, they identify 4 things that you need to answer when you're trying to build out a tree of thought. You need to have a mechanism to decompose into thought steps. So you can think of this as the steps in your chain of thought, your rationale. You need to be able to generate thoughts for each state. So if at a different node, I guess, or step in that rationale, you need to be able to generate new thoughts to continue that chain. Then you need to have a mechanism for heuristically evaluating that state. So is this currently a valid state? Is this moving me closer to an ultimate answer that I want or not? And you need a mechanism to search over the tree. The mechanism to search over the tree can be any of the existing tree-based traversal algorithms. So it could be a breadth first or a depth first search, or it could be an A-star algorithm. And by leveraging this, what enables us to build out is effectively this tree-like structure that has the chain of thought steps broken down as nodes that we can then traverse to get an ultimate answer. So I'll give an example of how this works using an adaptive variant of a depth first search algorithm. So let's say we have our input from the user and we have a prompt here, but has been omitted for clarity in the diagram. And we generate 3 possible thought steps. Then for each of these thought steps, we need to evaluate which one is the most promising. So we start with this light blue one, and this is done using our heuristic evaluator. In the paper, you can read some ways for heuristically evaluating them. One approach is, for example, and again, this could kind of be viewed as a tangent of self-criticism, is getting another large language model to evaluate each of these states. Let's say that the one on the left here is looking most attractive. I then generate the next steps, the next thoughts in this chain, and you can generate how many steps, I guess, or how many options you generate is a hyperparameter that you can set. You can also do pruning here. So for example, let's say I originally generated 4, but I pruned it down to 2 because the other ones were not valid, not worthwhile. And again, the process now goes where I have to heuristically evaluate the states. So I start here, I go here, but let's say I've actually done my evaluation and this isn't looking promising anymore. I can't go forward, or it's not worth going forward. So I now backtrack to this darker blue node and in the middle here, and then I go through the same process. So I generate the thought steps, I heuristically evaluate, I generate thought steps, I heuristically evaluate, and let's say I have a max depth for my tree. I've now reached my max depth and I'm at my best state. I return this as the answer to the user. So in general, we see here how we can break down this chain of thought approach into multiple steps. We can combine this with a data structure and use this to build out a data structure. And then we can apply existing algorithms to search over this data structure, or we can provide modifications ourselves for searching through it. Skeleton of thought is a relatively simple approach, but in general, it's a good reminder as well that a lot of these techniques, you can find ways to parallelize them. This is one way of parallelizing a language model generation. So what they do here is they have an input and their prompt. And what they do is say, identify the main points that you would need to answer to be able to answer this question effectively. You can think about this in other cases, like identify the main points that you'd want to discuss in an essay for this to be a good essay, or this to be a good product description. You now have this skeleton, which is the endpoints, and you execute n LLM calls in parallel to get expanded responses for each of those initial prompts, and then you concatenate them, or you could apply a more complicated concatenation strategy to finally get your answer that you return to the user. And so while this is faster, still have to take into account that there are multiple language model calls here. So it's worth evaluating when you're doing an implementation, how you can try and find ways to improve latency. Our final section today that we'll be discussing is alignment. So LLMs often struggle with ambiguity, and finding ways to, alleviate some of this ambiguity has been associated with performance improvements, and you should try and do it where you can. So one simple way that you can do this, and this goes again to some of the previous examples we've spoken about trying to make sure that we give representative examples, is we can provide, in a few shot context, ambiguous demonstrations. So let's say that you're doing a classification and you have something that's really quite hard to tell. What you can do is you can choose one of those examples where it's hard to determine what is the best answer. You annotate that yourself with what you determine as the correct answer, and you provide that as an example. The idea here is, instead of having the large language model have to try and guess what would be the best approach, you give it now explicit guidance on, when it receives an ambiguous example like this, how do you want it to behave? Okay, question clarification. This is, again, defined to reduce ambiguity. What we do is we have a prompt, our input, it goes to a large language model to generate an answer. And then we have this answer provided to another large language model whose role is to ask whether we need further clarification or not. So to classify whether the initial answer is satisfactory based on the information that was provided, or if there's further information that really should have been considered to generate a faithful answer. So assuming there's no further clarification required, you can return the output directly to the user. And if there is, what we do is we go to another large language model that generates a clarifying question. This is provided to the user clarifies, and then we provide that clarification to the large language model again to get the final output for the user. I've done here a single example, but you can see how this could be extended to be in a loop-like fashion, or how we have a set of, for example, k clarifying questions, and we go through all this process until we have clarifications for everything, and finally generate the answer. Prompt sensitivity, we've spoken about this a bit earlier in the presentation, but I think it's important to highlight again now, and that is that large language models can be brittle. The performance of them can be quite, I guess, variable depending on how you structure different things in your prompt. And being able to recognize and understand this will help you a lot in debugging and identifying areas where something has gone wrong, and a potential way for determining why it has gone wrong. So firstly, wording, and especially for the smaller, the less capable models, really small changes like using a extra space or using a different style apostrophe can actually significantly change the performance or the style of generations that you're going to receive. This is because the language models don't actually deal directly with the words or with the tokens with the symbols that you provide. What it operates on is tokens, and each large language model associated with it has a tokenizer, which has the purpose of converting these input words into tokens. And these tokenizers are trained on different data sets and to do a different approach to tokenization. So this can mean that a different space, for example, can cause a different token to be tokenized, which can mean the ultimate generation, which is conditioned on these tokens, will be different. And this can actually result in a lot of areas. I've seen production use cases before where the person, for example, that is doing the initial prompt engineering is different to the team that is actually deploying the feature. And when they've implemented the prompt, they've accidentally introduced another space, and then performance has degraded. We haven't been sure why, and then we've identified here that it's different. So how you can actually test for this is you can run the tokenization process, and you can compare the tokens because they're just numbers. This can be done quite easily. This can give you confidence that the template that you're using is the same and consistent between both. So further caveat here again, as models are becoming more performant, finding this to be less of an issue. But if you're working on a small model or something that potentially that you fine-tuned yourself, be wary of things like this. The problem format, so how you frame your task can impact performance. And a classic example here is if we are trying to detect, for example, again, let's say with let's detect whether a user is likely to churn. You can do this as a two-class approach, which is likely to churn, not likely to churn. Or you could ask for basically a single classification is this user likely to churn? And depending on how you frame that, whilst you're getting the same, I guess, outcome, it can result in different performance. So you should try out these different strategies and see which one works best for you. Sequence research has found that the order of the examples can alter performance. So again, be careful of your ordering, try out different orders. And a fourth thing to be aware of here, especially for people using commercially provided endpoints, that if a model is trained, so for example, if there is a continuous learning approach, or if they're continuously doing human reinforcement learning, then it can mean that a prompt that you used at one point in time no longer has the same outcome as when it is used today. And that is because the underlying weights of the model have changed, and this means that the outcome associated with it can differ. Let's now talk about calibration. So LLMs can be overconfident of their answers, and we have to be wary of this. So one example is Sycophancy. And research has identified, and you might have noticed this yourself if you've been using, for example, a ChatGPT, is that if you, convince the model, or you say, no, I really think it's right, it will often end up just agreeing with you and changing its additional answer. And this is worse for models that have had heavily been aligned based on human feedback. And emotional prompts, so appeals to emotion, can reinforce this issue. On the right here, we have an example of how you can induce this sycophancy. Next, let's talk about verbalized score. This is something that can be quite attractive as a technique that people want to employ when they're building an AI feature. And that is asking the language model itself to say how confident it is of its answer. So opposed to calculating an entropy or doing a majority vote, specifically asking the model, how confident are you? But it's important to be wary of this. There has been some research that has shown that this could be beneficial, but there has also been research that shows that a lot of the time it is overconfident, and you shouldn't rely on that. So in general, I would be careful of this approach and using it in production. Here is an example on the right of how you can request score verbalization from a model. Finally, let's talk about some of the biases, both that you should be aware of that are inherently there because of how models have been trained, and also ones that you can introduce when you are prompting a model and how you can remedy them. So the first area to consider is the training data. Again, these models are trained based on large corpuses of data, and based on what they have been trained on, they will predict different responses. Their weights will alter based on them. So for example, if a model was trained on a data set of 4chan posts, that is going to be very different to a model that was trained on academic papers. So to the extent that you can and it's available, you should review the data sets that was used to train your model and see what they were composed of, and try and identify if there are any biases that you think could be getting injected via that approach. Next is underrepresentation. And so this is both in the form of the training process itself and also in prompts that you provide. We've discussed similar things here, but how I want to highlight how this can be important is based on the core training process. If there are less examples of a certain, for example, a certain language, then the model will be biased towards performing worse for that model, for that example. So it might not necessarily be the case that it is biased in the sense that it's speaking negatively about a certain language, but it could be that just performance drops. So for example, for a lot of the large language models, they've been primarily trained on English data. That means that if you use them in other languages, performance will often be significantly worse. And so this would be an example of how underrepresentation has led to a bias in performance. This next one is now a strategy for how you can address bias by prompting. This is a synthetic data generation process, and effectively what we do is we try and identify attributes in a prompt that we think should be varied so that we can promote diversity and representation. And then we prompt a large language model to fill in different options for these placeholder variables. So we now build up a synthetic data set that has multiple representations and diverse examples. Cultural awareness. So there was some research done on translation tasks, large language model based translation tasks, and that they found that just asking and instructing it to use culturally relevant words actually improved performance for these translation tasks. Balanced demonstration. a bit similar to how we were talking about using representation and choosing examples that are aligned and similar to your output. Balanced demonstration means that you should try and choose examples for your few shot prompts that have been evaluated to be fair and representative of your users and of your data set. And this can be done empirically by using or defining your own metric for fairness, and then choosing examples that are ranked high based on that metric. Finally, an approach that you can use to reduce bias, and there's been found in some research to actually do exactly that, reduce the bias, is simply asking the language model to produce unbiased results. So this is a basic technique, again, that you can do in a zero-shot fashion. You can add as an instruction to your large language model prompt. Okay, so that has been an overview, a lot of the most popular techniques for prompting large language models. I hope you found this useful. If you have any questions or are interested in how you can apply these to help with your own AI problem, please feel free to send an email to info@aregoai.com. Thank you.